Hi, I'm Bob Tabor with Developer University. For more of my training videos for beginners, please visit me at devu.com. In this lesson, we're going to continue on with classes and object-oriented programming. We're going to talk about the lifetime of object references and how .NET manages the memory that your objects use. Secondly, we're going to talk about constructors, which are special little methods that run at the moment you create a new instance of a class, and we'll talk about why you even want to use constructors. And then finally, we're going to talk about shared methods and properties. Shared is a keyword. In other programming languages, it uses the term static, meaning that you can use that particular method or property without creating a new instance of an object first. So that would explain the console window and its difference from how it's different from the random object that we used in previous lessons. So let's go ahead and get started. And this is one of those cases where you probably want to use the code that I'll supply. You can find it wherever you're currently watching this video or wherever you originally downloaded it from. There is a folder called Before, and you should be able to find in the Before folder an object lifetime project, and you want to copy that somewhere on your hard drive. I'm going to put it where I put all my projects, here in the project subfolder of Visual Studio in my documents directory. Okay, so now let's double click the solution file to open up Visual Studio, and you'll see that I've already pretty much just copied the code that we worked with previously here to create a car class with the make, model, year, and color. And then you'll notice also in the module VB in the sub main, we're creating a new instance of the car, setting its attributes, and well, there's a little bit of something that we'll come to a little bit later. Let me go ahead and delete that for now. All right, so at any rate, what I want to do is actually focus on this line of code, line number 5. What's actually going on here? Well, the .NET Framework runtime, when it encounters this line of code, will have to go and create a spot in the computer's memory large enough to hold a new instance of the car class. So that's that bucket analogy we've been using. It's going to create a new bucket in the computer's memory large enough to hold a new instance of this custom class that we created, right? So the computer's memory has addresses in it, similar to the address where you currently live in your home or apartment. So admittedly, the addresses in a computer's memory looks a lot different than the address you might live at, 123 East Main Street, some city, some country, and then some postal code, right? It actually uses hexadecimal values as addresses, but they're addresses, they're known addresses nonetheless, and that's how the .NET Framework runtime knows where it put your buckets. It keeps track of the addresses, and it keeps track of the address and the little friendly label that you give it whenever you create a new instance of a given object. In this case, my car is at this address. It uses that address, looks up into that address in the computer's memory, finds the bucket, grabs the values out, and lets you work with them. Okay, so the .NET Framework's first job is to find an empty address where nothing else is being stored right now whenever you create a new instance of an object. And so that address has to be large enough in size to store a instance of our given class. So it creates the object, and then it grabs the address of that object and copies that address down. And so it always knows where to find that object in memory that we've labeled my car in this particular situation, so that you can always get back to that object in memory. And so you can store that reference in your variable, but really all you're doing is storing an address in that variable. And behind the scenes, the .NET Framework runtime knows what it means. It goes and finds the actual bucket at that location. Okay, so my car in this case is simply holding an address, or what we would call a reference, an object reference, a reference to the instance of the car class in the computer's memory. So whenever you need to work with that instance of the car class, you just use the myCar identifier. We can set and get attributes, we can call functions, and the .NET Framework takes care of the rest for us. Awesome. So it gives you this illusion that you're actually working with the object itself, but in reality, you're just holding onto a reference to an address in the computer's memory, and then the .NET Framework runtime takes care of all the rest and makes it hidden from you. So an analogy that helps me understand references to objects is kind of, maybe to extend the analogy of a bucket, a handle on the bucket. We've used the bucket analogy several times up to now. So whenever you store an object in memory, .NET gives you, the developer, basically a handle that allows you to get back to that bucket, so you can hold on to that bucket. All right. So what happens if you let go of the handle? Well, you'll no longer be able to get to that bucket. The bucket will no longer be accessible. Why will it no longer be accessible? Well, one of the missions of the .NET Framework runtime is to keep the memory region clear and get rid of stuff it no longer needs. And so the .NET Framework runtime goes through and cleans up memory every once in a while, and it does that by counting references, or counting how many handles you're actually holding on to. So if we're no longer holding on to a reference or handle to that particular object in the computer's memory, to the car class, then it's going to remove that instance of the car class from the computer's memory because it thinks we don't need it anymore. So it frees up that space in memory so that other programs can actually use that for their own needs. So this process of cleanup is called garbage collection, and there's a lot you can learn about garbage collection and how it works behind the scenes. Not all that important for the moment, but what I want to do is actually run a quick experiment. And I want to actually use that line of code that I accidentally left in a moment ago. So my other car as car equals my car. All right, so here we go. At this point now, we did not create a new car in the computer's memory. All we did was say, I want to create another handle, and I want to attach that handle to the same handle that my car is pointed to. So we essentially just copied the reference from my car to my other car. Now we have two handles attached to the bucket in the computer's memory at this point, okay? And to prove this, here, let me just show you how I can prove this. So console.writeLine, and we'll go my other car dot make. That should be sufficient to prove this to you. Then what I'm going to do is go my other car. I'm going to set the color from whatever it is to black. And then what we'll do is console.writeLine. We'll go my car dot color, just to see what color it is. Is it still white or is it something else? So this should prove that we're now dealing with two handles to the same object in the computer's memory. So let's also write a console.readline real quick here, and let's run the application. And you can see the first thing we get printed out is Toyota. So that was what we got from my other car, even though we never set explicitly the make attribute of my other car. Because it's referencing my car, it's able to grab out Toyota. And then next, we're looking at my car. We set its color to white, but since my other car is pointed at the same object in memory, we can set it to black, thus affecting the color of my car and setting its color to black as well. All right. So now you have two references to the same object in the computer's memory. And I think the important thing here is that you can create a variable that can hold a reference, but you don't have to create a new reference necessarily. You can just copy the reference from another object. All right. So another analogy that kind of helps me, because you don't think about multiple handles on a bucket, maybe you could think of it like strings on a balloon. After you cut the last string on a balloon, what happens? If it's filled with helium, it's going to float off into outer space and you never hear from it or see it again. All right. So the same is true whenever you're working with references here in your application. When the references go out of scope, in other words, whenever the current thread of execution of our application exits through the end sub, and it leaves the code block where the variable and the object of the object, the variable holding the reference to the objects in memory are actually defined, then we actually lose those references We're essentially cutting the strings off because we're exiting out of the application, or at least out of the scope of this method, and those variables are no longer accessible. The .NET Framework comes through and says, oh, hey, car class, it looks like nobody's looking at you anymore. Time for you to go away. And so it takes it and removes it out of memory. All right, so that is known as reference counting, to see how many references are still attached to a given object. The .NET Framework will count the references. If the references go to 0, the count goes to 0, then it will remove that object from memory. So at some indeterminate time in the future, after we exit out of the execution of our application, then the .NET Runtime with garbage collection feature will come around and will count references. It'll remove the objects in memory, freeing them up for other applications. Now, what if we wanted to explicitly remove our references? In other words, what if we explicitly wanted to cut the strings to the balloon before we go out of scope because we hope to use that particular variable again, or we're working with a lot of objects and we want to free up the memory? We can actually do something like this. So here I'm going to set my other car equal to nothing. All right, so when we set this equal to nothing, we're saying, hey, instead of pointing at something, point at nothing. So now if we were to try to reference and go console dot writeLine and go my other car dot, and we attempt to get the color out, let's see what happens when we run the application. We're going to get an exception that there's a null reference exception. There's a reference, but it's null. In other words, we don't know what it's pointing to. It's pointing at nothing. So we can't access an object that is pointing to nothing in memory. All right, let's go ahead and stop that. Now, if we were to set both of these to nothing, so my car equals nothing, we would actually probably kill off this line of code as well. And then at some future point in time, some indeterminate point in time, the object would actually be removed, but it doesn't really matter from a practical purpose because we don't have any access to that object in memory anymore. So in some situations, this indeterminate amount of time, because the garbage collector will run whenever it feels like running, there are some rules and memory pressure that force it into action, and otherwise it will just be dormant. But if we need to be specific about removing objects, and we want to be explicit about removing objects from memory because we have a very memory intensive application, we can do something called a deterministic finalization approach that allows us to say, hey, stop everything you're doing .NET Framework Runtime and remove it now. And we might want to do that in situations where we're holding on to some connection, maybe to a network resource, to a database, to a file, and we want to sever that and make sure that at the moment that we say we want it to be severed, we want it to be actually severed so that it frees up that resource so something else can actually use it. So that might be a scenario where we would want to be very specific about it removing that object from the computer's memory, but otherwise we can just let the .NET Framework do it on its own and not really worry about it. That's a little bit more of an advanced concept. We're not going to cover that in depth in this series of courses. However, if you were to search for the words deterministic finalization online, you'll find some articles about it out on MSDN, maybe even some videos. All right, so the next thing that I want to do is focus on the little subtle usage of the opening and closing parentheses, because hopefully there's something about that should jump out at you. And that little something is the fact that we're actually using the method invocation operator here whenever we create a new instance of a class. So whether you realize it or not, whenever we create a new instance of a class, like the car class, we're actually calling a method called a constructor. And it allows you, the developer, the option to write some code at the moment that a new instance of our class is instantiated, that moment when that new instance of the class has been created in memory. We can write code at that point to do things like, for example, put the object itself into a valid state. just like we would any other initialization that we've used for other variables or even the array, as we learned earlier. So this means that we can use our the special constructor method to construct or initialize the values of properties so that our objects are ready to be used on the very next line of code. You may not always be able to do it that way, but it's definitely an option to use. So I want to create a quick example here of why you might create a constructor. And that'll allow us to set the properties of the car at the moment whenever we create a new instance of the car. So to create a constructor, you use the public sub and then the new, and the new keyword represents a constructor. So here I'm going to do something like maybe I would load this from a configuration file to populate the make, the model, the year, and the color. I might actually load it from a database, or maybe grab it from online somehow. But in this case, what I'm going to do is to actually hard code the make property so that by default all new instances of the car class will automatically be or have its make property populated with a real value. All right, so here what we'll do is just say make equals, and then we'll say Nissan. Okay, so now whenever we create a new car, what we can do right away is console.writeLine and then look at my car dot model, or was it make? I think it was make, sorry. And you can see that initially, by default, the car is in a valid state, setting its property to Nissan. Of course, then we cover that up by setting it equal to Toyota and print it out a little bit later, but at least you get the idea of how you can use it. Now, admittedly, this doesn't make a whole lot of sense right here. I'm just showing you the technique that you would use, not really the rationale. But let me show you an overloaded version of a constructor. So like you created an overloaded method in one of the previous lessons when we talked about methods, and you did that by creating different method signatures, you can do the same thing with constructors as well. The method signature, you'll recall, is the number and the data type of the input parameters. So we can create a second public sub new, and as long as we change the method signature, so at least in this case add one input parameter, then we'll have a different version of our input parameter. Will be two different ways that an object can be created. So let's do this by val, and then I'm going to do I'll use a underscore. Now I'll just call this the make value string by val model value string by val year value as integer, and then by val color value as string. Okay, and then here what we would do is just do a mapping from make equal to make value model equal model value, year equals year value, and then color equals color value. All right. So now, whenever we create a new instance of car, and let's just do that here, for example. In fact, let me just comment out everything here so far. And we'll essentially do all of that in one line of code. So dim my car as new car. But notice now I have two versions of my constructor. the first version will accept no input parameters, but the second will accept 4 input parameters: the make, the model, the year, and the color. All right, so here we go. Let's go Toyota 4Runner 2010 and white. All right, so we're able to now run our application. In fact, yeah, let's go ahead and run it. And you can see that we still get Toyota printed out. Why is that? Well, because we were able to use an overloaded constructor to pass in all of the values we wanted to populate at the time of instantiation instead of doing it in subsequent lines of code. All right. Just to kind of reinforce the overloaded nature of it, we can't create another overloaded version without any input parameters. Why? Because there will be multiple definitions with identical signatures. All right. But I do want to say this. If we were to remove this version that accepts no input parameters, what happens then when we go back to this line of code? Well, whether you realize it or not, there is a default constructor. Now in this case, because we have at least one constructor defined here, let me comment that out, we get a complaint. But once I get rid of that, notice that we're able to call the default constructor, and it doesn't really do anything. But if you were to look at the code that's generated, the car class will have an empty method called new, and it will call that. Nothing happens, but just know that behind the scenes there's a default constructor that's always created for your classes. So you can always use the method invocation operator after the creation of the instantiation of a new class, and you can know that at least it will work. It won't throw an exception. However, once you declare a single version of a constructor, then from that point on, you won't be able to use it because the default constructor will be covered up by your new constructor. All right, and furthermore, even if you were to create this version like we saw earlier, it will cover up the default constructor as well. All right, finally, I want to talk about another keyword called shared. And what you can do with the shared keyword is to create methods, especially methods, but also properties that do not require you to create an instance of the class in order to use them. So many times classes that we're going to work with related to building .NET applications, they don't require that you create a new instance of them first in order to start using their methods. And a good example of that is the console class. We didn't have to create an instance of console. We just started using the methods of the console class like writeLine, readLine, clear, and others. So another example, when we were working with arrays, you remember I used the array.reverse method. We didn't have to create an instance of the array class. We just started using the array.reverse method, and you typically would use this whenever you need methods, but you don't really need to keep the state of an object. You just want to collect together a bunch of utility methods that do something in your system, but they don't rely on a specific instance of a class in order to operate. writeLine, readLine, clear, they're all available by just referencing the class name console, because when Microsoft created those methods on the console class, they marked them with the shared keyword if they were writing it in Visual Basic. All right. So you can create your own shared methods as well. And so our objective here at the outset is really just to utilize the .NET Framework Class Library and understand the difference between a shared versus an instance class. So there's instance methods and there's shared methods. There are instance properties and shared properties. For the most part, up to this point in the car class, we've only used instance methods and instance properties. But what I want to do is create another class, and I'm going to call this public class carlot. And here what I want to do is create an add to inventory method. So public sub add to inventory, And what we'll do is go by val, new car as car. And then I'm not going to implement the body of this because we really don't have anything at this point that would help us with this. But the body of the method goes here. I might save this instance of car in an array, or better yet, in a collection, which we'll learn about later. Okay, but the focus here will be just on the fact that we can mark this with the shared keyword. And now notice in our module1.vb, what I can do here is go carlot dot add to inventory. I didn't have to create an instance of carlot because the add to inventory method is shared across all instances of carlot. It doesn't depend on an instance. It's shared. So in this case, I would just pass in like my car, and then it would perform whatever operations on it. You might also notice that I was able to define a second class inside the same file. I typically would want to move those out into their own files, but for such a small version of a class, I can just create it right here inside of another file. Okay. Now, why you might want to use the shared keyword, that's a little bit more complicated. It might require a longer discussion of design patterns and coding heuristics. Again, I just want you to know that it's available. And more importantly, I want you to know that you're going to encounter shared methods as opposed to instance methods like we created previously, and then also with our constructor. You're going to encounter them in the .NET Framework class library. And then why you would actually use this inside of your own application might not be obvious now, but you can pick that up a little bit later as you're designing your own code libraries that other developers on your team might utilize. So it's not really important why you use them just yet. Just know that they're in use in the .NET Framework class library, and there's a reason, and we're not going to talk about that reason in this series. Okay. So let's recap what we talked about. In this lesson, we talked about the lifetime of an object, including what happens when there are no more references to an object in memory, and how the .NET Framework runtime employs garbage collection to remove objects at some point during the execution of the application. We looked at constructors and talked about when they're actually invoked, how to create an overloaded version of a constructor. We talked about the default constructor and why it's not available if you create any other version of a constructor. And then finally, we also looked at the shared keyword, essentially to create utility methods inside of classes so that we don't have to create an instance of the class in order to utilize that particular shared method. And we've seen instances of this all over the place whenever we were working with the console class, the date class, and so on. All right, and you'll continue to see those in the .NET Framework class library. That's the important part. All right, so if you don't completely understand the notion of shared or any of these other ideas, just I would say for now, just go ahead and continue on. Just understand basically conceptually what it is, and we'll learn a lot about some of these other concepts as we continue to move forward. Okay, so let's continue on the next lesson. If you got this far and you're with me, you're doing great. We'll see you in the next lesson. Thanks.